Okay, well, this is perhaps one of the best pictures you can get out in the Stillwater complex. It's not a particularly photogenic one. This is a picture of the inch-scale doublets. It's layered intrusions. For those that don't know those, these are magmas that intrude into the shallow crust of the Earth. As they cool and crystallize, they form a layer cake stratigraphy. In this case here, that stratigraphy has been tipped to near vertical. I do want to mention, based on what we were talking about earlier, that this outcrop is slowly being degraded, not from mining or development activities, but from dozens, if not hundreds, of geologists every year pounding on it. And over the course of my lifetime, it has been significantly knocked down. So I would like to suggest that you and all your students, when you're at a site like this, take pictures, not samples, unless you're doing real science. Okay, so where are we? Why is it important? This is one of the world's largest layered intrusions. It also has one of the world's highest grade platinum group element deposits. And as such, it's a laboratory for understanding igneous processes broadly construed. Where is it located? Dave already talked about the ancient terrains that we get in the western United States. Again, as part of the Wyoming Craton. Dave was talking about the Beartooth, where here's the Beartooth block here. The Stillwater block is along the northeast side of it, been pushed up by laramide structures, so we can see pretty much the whole thing here. This is what it looks like in the geology. It's about something like 40 kilometers long, maybe about 6 kilometers in its maximum thickness. We can see the bottom of the basal contact, if you will. But the upper part was eroded sometime in the Precambrian, and it's now covered with Cambrians and younger sediments. So we're only seeing a piece of what was probably a much larger intrusion, probably about the size of the Bushveld complex down in South Africa. Geophysics and xenoliths brought up from more recent volcanic eruptions suggest that it continues considerably to the north. This is the section we see through it here. So this is here's some of these earlier granites and all this metamorphic terrain. We do get a fairly sizable basal metamorphic aureole at the base of the complex. Then we get into the complex itself here. You get an ultramafic zone where it's basically just olivine and orthopyroxene with some chromites in it. And then in the banded series, we start to pick up plagioclase, as shown over here, and we get a number of different rocks over here. So basically, kind of what kinds of rocks do we get in here, and why is it important here? We have chromite deposits throughout here. They're labeled from A through K. The largest one is the G. This is a fairly modest one right here, shown right here, but it's one of the more photogenic ones here. This was never mined commercially for chrome, but it was mined under government contracts in the 40s to early 60s, largely to make a strategic chrome reserve here. Okay, and then we have the JM reef, all right? This is not a reef in the kind of classical sense that a sedimentary petrologist might think about here. Reef is just a South African mining term that means a mineralized vein, if you will, here. And this is what it looks like out in the field. Not too particularly exciting for a world-class platinum deposit, which is probably why it took them 50 years to find it. The rocks don't look like much, and even when you do want to see something, you usually want to look at a somewhat weathered rock, and you see that it's a mixture. In this case here, some olivine-bearing rocks and more plagioclase-rich rocks here. Now, why is this important here? Well, besides being a very important ore deposit, is we want to know what is the process that causes something that's in the parts per billion concentration in a magma to get kicked up into the a few tens of parts per million range, basically a 3 to 4 order magnitude enrichment here. And there's a lot of different models. We're still arguing over them today here, but I'll show two. One is what might be called the Downer model, okay? And this is an orthomagmatic model here. And basically what happens is you have a new magma intrudes, maybe it's a very light magma, it goes towards the top of the magma chamber. For reasons of chemistry changes, it becomes sulfur saturated. That sulfur precipitates and rains down through a fairly thick column of magma, and that acts as a collector and makes an ore zone at the top of the crystal pile. Okay? This is called the Downer model for obvious reasons. The sulfide is acting like a collector, like rain might clean pollution out of dirty air. It may also be bringing in some of the olivine as we see here. Okay? At the other extreme, we have the upper model, and this was the idea is that ore metals are moved upward by some sort of a vapor refining process that's occurring within the crystal mush as it's forming and growing. So you have a crystal pile here. The lower parts that are near the lower contact, they're more solidified. The interstitial liquid there eventually becomes vapor saturated. That vapor saturate moves upwards, carries ore elements up with it, and you get an ore zone formed this way here. Some of the evidence for this is the very coarse textures we see in these rocks here, and this one here is known broadly as the upper model. So you have the debate between the uppers and the downers here. Some of the evidence for a fluid roll, and this is, I should mention, the Stillwater became fairly important for understanding how a fluid model would work, includes the unusually chlorine-rich composition of the apatites. Prior to some work that was done late 80s, 1980s, early 1990s, it was discovered that the JM Reef in the Stillwater complex and the rocks below it, the apatite, is extremely chlorine-rich, okay? Subsequently, it's found that the same deposits in the Bushveld complex in South Africa are also very rich, and we see a kind of a crude association of the more chlorine-rich systems, something you would expect in a chlorine-bearing fluid, to be richer in the PGE than in other ones here. These are more typical of what we see in terms of the chlorine apatite compositions and other intrusions. The other is the presence of a lot of other hydrous minerals such as biotite, and even as biotite and amphibole included in chromite from the zone here. And in this interpretation, the olivine is actually due to an incongruent partial melting driven by hydration of the rocks here. So, two extremes, we're still arguing on what's actually going on here, okay? Other things that are interesting from the intrusion are some thick anorthosites that occur in the upper part of the intrusion. The thicker one here is about 600 meters thick. And these have been used as analogs for understanding the formation of the lunar highlands, which are also anorthositic. And the idea in both cases, well, in the case of the lunar highlands, the idea is when the Earth or the Moon first formed, you had a magma ocean around it, and the plagioclase basically just floated to the top of that and formed a scum on the surface that now forms the cratered lunar highlands. And the same thing was idea that came from in the Stillwater complex, in that this constant plagioclase constant that we're seeing here is basically just the equivalent that was crystallizing, what would have crystallized and collected with in the ultramafic series if it had settled for some reason here. Okay, scientific tradition. There is a long history of understanding the geology and the ore deposits and layered intrusions. This is a group going back from 1932. This gentleman here is Art Howland. He was the first to describe platinum group metals in the 1930s, but as I said, it wasn't until later in the 1970s that we actually discovered the JM Reef. Okay. It's also interesting for other kinds of processes that go on. And in the last 100 years or so, there's been something like 600 or more Stillwater-related publications dating back to the late 1800s, with many of these from researchers based around the world. And here I get back to the inch-scale doublets here, which are basically pyroxene pairs that occur in a more north-acidic matrix here. And this is an example of pattern formation that can occur during simple just crystal aging of a partially molten system here. So the main arguments for inclusion in the IUGS program here, it's an important laboratory for understanding a host of igneous processes and magmatic ore deposit models. Thick anorthosites, as I said, are analogs for understanding the origin of lunar anorthosites. And there's a continued controversy over the role of high-temperature hydrothermal processes versus conventional magmatic interpretations for mechanisms concentrating things like chrome and the platinum group elements here. And it also is related somewhat to the timing of stabilization of the cratons at 2.9 to 2.7 billion years ago. And getting back to a point that Dave made here about possible subduction at this time, we do see that that chlorine that I was talking about actually has a crustal signature to it, which may have been due to fluids being driven off a descending slab that's adding crustal chlorine into the mantle regions. So that's it. Thank you.